All right, we shall get started. And let me just, so today we are going to continue on. We're going to go into chapter 9. And I realize maybe my class is moving on at a little bit of a faster pace than what you previously had. But I think at least this way we'll cover what I feel is necessary for an introductory statistics class. So let me pass out some reference tables. Do you guys already have T-tables?
Yeah.
Oh, you do?
You sent it to us.
I sent it to you guys?
Well, it's part of the homework link.
Okay, that's part of the homework links. Okay, well, if you don't have a T-table with you, then let me pass these out. Okay, so, all right, okay. Let me just pass these out here. And if you don't want to, oh, sorry, I'm not trying to step on your feet here.
I printed it out, but I'll take one. I like that. I have to say that I really like the DF name, the degree freedom. How much degrees do
There's no such thing as perfect freedom.
Exactly, that's what I mean.
Yeah, I guess you actually have more data on the topic of something my degree of freedom is going down.
Oh gosh, well mine in about 2 weeks is going to be a lot of the white spread and then less precision. So I'm gonna pass
Worry
this
about
out.
that later.
It's just
All right, so in chapter 9, we will continue on with confidence intervals and hypothesis tests. So last week in chapter 8, we covered confidence intervals and hypothesis tests. But what kind of data were we comparing? Categorical data. And these were confidence intervals and hypothesis tests for proportions. So it would be something like, is the proportion of I don't know, men who go hunting the same as the proportion of women who go hunting, okay? And we can do a hypothesis test, and maybe we'll survey, maybe we go to a state where they do a lot of hunting, so like Wisconsin or something, and we say, we survey 200 men in Wisconsin and ask, do you guys go hunting or not? And then we ask 200 women, or they don't have to be equal numbers. But maybe we ask 200 women, do you go hunting? And some of the women say yes, some of the men say yes, and then we compare the proportions, and we ask, is there a difference in proportions? And if we did statistical tests, would we find evidence of a difference in proportions? So that was the hypothesis test. That sounds familiar? Nod your heads, yeah? Okay. In chapter 9, we're continuing on, except we are not talking about proportions anymore and dealing with categorical variables, but we are dealing with quantitative variables, and we are comparing means of groups. So in chapter 9, we perform hypothesis tests and create confidence intervals for quantitative variables. Okay. So a quantitative variable can be summarized using what measure? If I gather a sample and I want to summarize this sample, what would I say? Okay, well, sample size is important, but how can I just summarize a set of 10 numbers per se? Using the mean, okay? So the main quantity or the main statistic that we will be using here is that we will be using the sample mean. All right. So for our first step, or our first thing of inference, we'll talk about a confidence interval for the sample mean. Let's create a confidence interval. So the idea behind this is there's a population from which we want to estimate the population mean. Okay, so we have no idea what the mean of the population is, but we want to create some kind of estimate for it. So the way we're going to do this is we're going to gather data, look at a random sample, and based on what we see in the sample, we're going to try to make a statement about the population mean. Okay, so for example, let's say we wanted to know how much TV the average person watches. Okay, so of course some people watch 0 hours of TV. Some people maybe watch 10 hours a day. Okay, there's a huge range. But how much does the average person watch? Is it an hour a day, 2 hours, half an hour? Who knows? Okay, so we want to create an interval for how much the average person watches. So ideally we could survey everybody, let's say our population of interest is the United States. Ideally we could survey everybody in the United States, but we can't, okay? There's 300 something million people. We can't survey everyone. So instead we deal with a sample. Okay, so now we want to say how much TV does the average American watch? Okay. So the only way we could get a definitive answer here is by surveying all Americans and asking how much TV do you watch. We add those numbers up and divide by the number of people we asked. Okay, that's the only way to get a true answer. Okay, the true answer. Okay, it would be ask all Americans and take the average. Take their average of their answers. That's the true answer, and the symbol for that is mu. That's the true average. But we cannot get this true average value mu. The best we can do is get a sample average. Okay, we cannot. Everywhere. So we ask a sample. And from, let's say we ask 100 people. So here's an example. N is equal to 100. And let's say the average, I have no idea. I'm going to just make up some number. 1.85 hours per day. This is the average after asking 100 people. Is this okay? So based on what we see in the sample, what can we say about all Americans? Yeah, so this is what we see in our sample, okay? So assuming this is a random sample, okay? So if this is a random sample, our conclusion would be that the average American watches something around 1.85 hours of TV per day. Maybe it's more, maybe it's less. We're not entirely sure. Okay? Does this seem familiar in terms of the thinking here? Okay, it's similar to a confidence interval that we made for proportions, right? We wanted to know the proportion in the population. We can't study everyone in the population, so we deal with the sample. And from the sample, we make an inference about the population. Same thing here, but now it's a quantitative variable. Okay, so if I were to make a confidence interval, what do you think goes in the middle of the confidence interval?
Sample mean.
The sample mean, x bar. X bar goes in the middle. Now I would go, how would I modify this or create a range here?
Critical value.
Okay, so I would say plus or minus some margin of error, correct, right? Okay, plus or minus the margin of error. And how do you think we're going to make the margin of error?
Standard error.
Standard error times a critical value, okay? So I got a critical value times the standard error. So this is very, very similar to creating a confidence interval for a single proportion. Can we see that?
Mm-hmm.
For a single proportion, what goes in the middle instead?
P hat.
P hat. So if we're dealing proportions, it goes P hat goes in the middle, and then it's plus or minus a critical value times the standard error. Same thing for means, except now we're dealing with x bar. The sample mean goes in the middle, plus or minus critical value times the standard error. Okay? But this is where the details change. Here, when we did proportions, the critical value was some number like z equals 1.96 or z equals 1.645, or I gave you some numbers, right? When we're dealing with sample means, you don't have those numbers anymore. You have to look up the number on the t-table, which I just gave you. And you can see at the bottom of the table, there's confidence level. And we would use these numbers to determine what number to use as our critical value. The other part that we have to figure out is our degrees of freedom. Okay? So the degrees of freedom depends on our sample size. So we need to determine the critical value. Okay, the critical value we call T star because it comes from the T table. The critical value T star, we need to know the degrees of freedom and the confidence level. Degrees of freedom, which are DF, and the confidence level. Is the term degrees of freedom familiar or completely new to you? New. Okay. The idea behind degrees of freedom is, let's say we can play a game where we're going to pick 10 numbers, and I can make sure, absolutely sure, that the mean of these 10 numbers will be 50, okay? And I can let you guys, how many numbers can I let you guys pick? I can let you guys pick 9 numbers, and as long as I get to pick that 10th number, I can guarantee that the mean of these 10 numbers is 50. Does that seem reasonable to you? Okay? Now how would I do that?
So that's where n minus 1 comes
That's where
from.
n minus 1 comes from, okay? So if the mean of these 10 numbers is going to be 50, the sum of the 10 numbers has to be what? Huh? 500. 500, because to get the mean, I just take the sum of the numbers and I divide by 10. So if the sum is 500, then the mean of the 10 numbers will be 50. Okay? Now what I can do, so if you get to pick the first 9 numbers, I just have to pick the 10th number so that everything adds up to 500, even if that number is negative. Okay? And then we do that, the mean of the numbers ends up being 50. So the idea for degrees of freedom is that you guys you are free to pick 9 numbers. As long as I get to pick one, I can guarantee the mean. Okay? So here, the degrees of freedom is equal to n minus 1. It's our sample size minus 1. That's our degrees of freedom. So in this story, or whatever, if we're trying to figure out the amount of TV the average American watches, how many degrees of freedom do I have?
99.
I have 99 degrees of freedom. My sample size is n equals 100. 100 minus 1 is 99 degrees of freedom. So in this case, I have degrees of freedom equals to 100 minus 1, 99 degrees of freedom. Alright, so if we have to look up our critical value here, and I say, let's make a 95% confidence interval, what I would do is I would go to the column where it says 95%, and then I would go to the row that says 99 degrees of freedom. But there's a problem. What's the problem? There is no row that says 99 degrees of freedom. Okay? So if you're ever faced in a situation where you cannot find the exact degrees of freedom, always round down. Okay? And it seems like, oh, but there's 100 degrees of freedom right there. Don't use 100 degrees of freedom. Use the next one that's closest, 75 degrees of freedom. I know it's like, oh, but 100 is so much closer. No. Okay? Always round down. Okay? You have to think, there. Okay, so round down to 99. So you can't find 99 degrees of freedom, so round down to 75 degrees of freedom. So in this case, we will use 75 degrees of freedom. But if you have a table that actually has 99 degrees of freedom in it, use 99 degrees of freedom. Okay, so this is just only use it if you have a table that doesn't have all of them and you can't find your thing. Okay, is that good with everyone? All right, so what is my critical value that I'm going to use here? 1.992. So my critical value here, my T star, is equal to 1.992. That's my critical value. And the standard error is going to be S divided by the square root of n. What is S?
Standard deviation.
The standard deviation of what? Of the sample. The sample standard deviation. So I actually did not give that to you here. So let's say our sample standard deviation is 2.2. Yes?
How do we know which confidence level?
I just said if we did a 95% confidence
Okay.
interval. Okay? Now, for a test or something, it will tell you what level of confidence to use. Okay? The most commonly used one is 95%. Also common are 90%, 99%. 98% is pretty common too. Okay? If I wanted to be 100% confident, what would I have to say? Huh?
0 to 100.
Yeah, actually, negative infinity to positive infinity, okay? The 100% confidence interval goes from 0 to 100 only when we're talking about a percentage or a proportion, 0 to 1. But when it's talking about the mean, what's the mean number of hours of TV somebody watches? Well, in that case, you can't have negatives, so it'd be from 0 to infinity, or maybe 24 hours a day, okay? We could be 100% confident about that. But in general, from negative infinity to positive infinity. So that's useless again, so we go maybe 95% or something. So what is my standard error in this situation? If I tell you, I just made up this number here, s is equal to 2.2, my standard error would be,
0.22.
it would be 2.2 divided by the square root of 100, okay? My sample size is 100, so I do 2.2 over 10, which gives me 0.22. So my standard error is 0.22. Alright, so let's put all those together and make our confidence interval. So I'm going to replace these and say x bar times t star times the standard error, which is s over the square root of n. I got 1.85 plus or minus 1.992 times 2.2 over the square root of 100. Okay. Anyone want to tell me what this number is going to be? 0.438. So on the upper end, I have 2.288. And 1.412. So this is my 95% confidence interval. For what?
For mu,
For the mu, and what is mu?
the mean of the whole population, television view.
Yeah, so for the hours, for the average amount of TV. The average amount of TV America watches. Okay? So if I wanted to complete this sentence, what would I write? I am 95% confident that the mean number of hours of TV Americans watch
Falls in the interval between.
is between 1.412 and 2.288 hours. Okay, so we're somewhere between 1.4 and 2.3 hours. Okay, that's what we would say if this was the data we gathered. Okay, assuming this is a random sample, and it looks like that. Is it possible that the average amount of TV America watches is 3 hours?
No. I mean, it's not within our confidence interval.
Okay, so 3 hours is not within our confidence interval. But technically it is possible. It's just incredibly, if it really were 3 hours, it's just incredibly unlikely that a random sample of 100 people would give me an average of 1.85. That's what that means, okay? So technically it is possible for it to be 3 hours, but it would be incredibly unlikely that our sample of 100 random people gives me an average of 1.85. So we would say we have evidence that the average amount of TV America watches is not 3 hours, because 3 hours is not in the confidence interval. So we can say we have evidence that it's not 3 hours, but technically it is still possible, okay? Just our evidence just shows that we'd be really surprised if it were. Does that make sense? Okay. Do we have evidence that the average amount of TV is not 2 hours a day? Why not? Why would you say we don't have evidence? Because 2 hours falls within our confidence interval. Okay. Is that concept clear to everyone, or should I write it on the board, or write it on the board? Okay. So we would say, so based on our confidence interval, we have evidence that the average amount of TV America watches is not 3 hours per day. Why? 3 is not in our interval. On the other hand, we do not have evidence that the average amount of TV is not 2 hours per day. Okay, 2 is inside the interval. Let's table that. Be in trouble in a fire. Okay. Good? Alright. So the important thing is that the concept behind a confidence interval is, in my opinion, not incredibly difficult. The hard part, though, is knowing, am I dealing with proportions and should I be using p hat? Or am I dealing with means and should I be using x bar? Okay? You got to be able to read a problem and identify when you're using proportions and when you're dealing with means. When do we use proportions? Categorical data. And when do we use means? Quantitative data, okay? So if you've come this far in your course and you cannot tell the difference between a categorical and quantitative variable, you are in big trouble, okay? So make sure you can read and figure out if something is categorical or quantitative. Okay. So that's a confidence interval for a single mean. Yes?
Can you just say why, again, why 2 cannot be, you don't have evidence that the average amount, even though it's in the interval, please?
Yeah, so 2 is in the interval, so we don't have evidence that the average amount is not 2 hours. It's, okay? Would we ever say we have evidence that the average amount of TV is 2 hours?
No.
No, we would never say that, okay? Because my sample average was 1.85. That doesn't prove that that the average amount of TV that America watches is 2 hours. It doesn't prove that it's 2.1 hours. It doesn't prove that it's 1.7 hours, okay? All of those values are within my interval, but it doesn't prove that the average amount of TV is this number, okay? All we can say is the number 3 hours Probably not. We have evidence that it's not 3 hours because 3 is not in my interval, which is from 1.4 to 2.28. On the other hand, can we say that it's not 2 hours? No, we can't say that it's not 2 hours, okay? It's a double negative, okay? Because 2 is inside the interval, so 2 is very much a plausible number, but it doesn't prove that it is 2, okay? So that's all we're saying. Okay. That's what we've got for confidence intervals. All right. And the flip side is doing a hypothesis test. Okay. All right. So take good notes here, and I'll teach you guys the stuff, and then we'll try an example and see if you can apply the stuff you just learned right now. Okay. For a mean, okay, based on one sample. Okay. Later today, we're going to do confidence intervals and hypothesis test for means based on 2 samples. So that's why I've got this thing right now here. I know, I'm covering quite a bit, but it's good stuff. Good stuff here. Okay. Okay, so when we did a confidence interval, it was, here's some data. Let's see what the data says about the population. Okay. When we do a hypothesis test, okay, and I think I'm telling something similar as when I did the proportions. When we're doing a hypothesis test, it's similar, but it's different, okay? Here we're saying, could the mean of the population be this particular value? Okay, is the mean of the population this particular value? Here's the data. And we're going to ask, if the population mean were this particular value, what's the probability that my data gives me these results? Okay. Similar to when we did proportions, where we said if the proportion of the population is this number, what's the probability that my data shows these results? And here we're going to do it for a mean. So here's an example. Okay. All right. So let's say you get into an argument or whatever. Okay. So let's say someone says, "Hey, you know, I went to Norway, and man, everybody in Norway is so tall." Okay. And you'd say, "Really? How tall?" And they'd say, "Oh, I bet the average height height of a man in Norway is 6 feet tall." Okay. And you're like, "That's really tall. I don't think it's 6 feet tall." Okay. So one person says, "I just went to Norway, and I think the average height of a man in Norway is 6 feet tall." And you're like, that seems a little unreasonable. Okay. I would wager that it's not actually 6 feet. I would wager that it's less than 6 feet tall. And you say, no, it's 6 feet. No, it's less than 6 feet. Okay. So you say, okay, well, we'll settle this the only way we know how to do. And we're going to go to Norway and collect a random sample of people. Okay. And so we go to Norway, and then we somehow manage to get a random sample of Norwegian males. Okay. They volunteer for this, and we get good results here. Okay. So maybe only 20 people signed up. Okay. And let's say the average height of the 20 people, their average height was 5'11" 5'11". So it was 1 inch shy of 6 feet. Okay, so I'd say, see, 5'11" is shorter than 6 feet tall, okay? Would we say this is evidence that your friend's claim is wrong?
No.
No, maybe, maybe not. Okay, well, we have to do the statistics before we can say yes or no, okay? And we will see, all right? So in this clip, so let me just write this up here. So someone claims the average height of a man in Norway is 6 feet, okay? So 6 feet is 72 inches. It's about, what is that? 190 centimeters? I have no idea, okay? For those of you in the metric system, okay? And then you say, I think it's shorter. I think the average height is less than 6 feet. Less than 6 feet, okay? Less than 72 inches. Okay? So we gather data. Okay? So in this case, our sample size is 20. We surveyed, we were only able to select 20 random males, and the average height of these 20 random males was 71 inches. And let's say we had a standard deviation of 3.2 inches. So do we have evidence that the average height is not 72 inches? Or is, not that it's not, the average height is less than 72 inches. Okay. Alright, so I'm glad that a lot of you guys, just at first glance, kind of shook your head and said no. Okay? And so now you're starting to understand the role that variation plays. Okay? Because back in 5th grade, maybe if you did a science fair project and you said, oh, you know, we're gonna, I don't know, measure something with this and measure something else with this, okay? Like we're gonna measure the plants that grow with just water, and we're gonna measure how much the plants grow when we add fertilizer to it, and see, and maybe you had 3 plants over here and 3 plants over here, and the average over here was they grew an average of 5 inches, and the average over here was that they grew an average of 6 inches, okay? And then at the end of the science fair, you'd say 6 inches average is bigger than 5-inch average, therefore fertilizer makes your plants grow taller, okay? But I'm glad, I'm happy that when I said your friend claims that it's 72 inches and we gathered data, and the average turned out to be 71 inches, is this evidence that it's not 72 inches? And a lot of you guys shook your head, okay? Well, the truth is we can do a test, but at least you're starting to see that maybe just because 71 is not 72 is not proof that it's different, okay? So if I were to set up hypotheses, what would my null hypothesis be in this situation?
Mu equals 72.
Yeah, that mu equals 72, okay? So we're doing a hypothesis test, and we're dealing with means here, but the thought process and the pattern of thinking is the same thought process that we went through last week, okay? The only difference is that we're not dealing with proportions, we're dealing with means. So when we're talking about the mean of the population, the symbol we use is mu, okay? This is the mean of the population, and the null hypothesis is that the mean of the population is 72 inches. And the alternative hypothesis is what?
And it's not.
Less than.
Is that the mean is less than 72 inches. Alright. So do you guys remember what it means to have a less than sign here? What kind of test is this going to be?
One
Left
tail.
A one-tail test, okay? Or one-sided test, or as you said, left tail, okay? But we'll just say, because it's a less than sign, it's going to be a one-tail test. Okay, because of the less than. So we have evidence that the average height is less than 72 inches. Okay. All right. So if the null hypothesis were true, anytime I take a random sample, what would I expect the mean of my random sample to be? 72. If this were actually true, anytime if the average height of Norwegian males was actually 72 inches, anytime I take a random sample, I would expect the average to be about 72 inches. So if the null hypothesis were true, we expect x bar to be 72 inches, okay? But what is our x bar? Our x bar is 71 inches. So is this difference of 1 inch, is it significant or not? That's what we're asking. Okay. My test statistic, okay, if this were the normal model, in the middle I would put 72 inches, and I'm actually down at 71 inches. What would my test statistic be? Well, I would take this difference and divide by what? 2. So if I had if we were talking about a z-score,
By the standard error.
I would divide by the standard deviation, or in this case, the standard error. What is my standard error in this problem?
3.2.
Over the square root of 20.
3.2 over the square root of 20. Okay, so our standard error, when we're dealing with one sample mean, is s over the square root of n. Okay. So in this case, it's 3.2 divided by the square root of 20. Zero 0.7155. 71554. Okay, sure, we'll leave it like that. Okay, technically we don't call it a z-score. We call it a t-score because it's the t distribution. Okay, but we'll just say our test statistic is always what we observed minus what comes in the null hypothesis divided by the standard error. All right. In the null hypothesis, our mu is supposed to be 72 inches. What we observed is 71 inches. So according to the null hypothesis, this should be 72 inches. And my standard error is what? 0.71554. So this turns out to be negative 1.398. How do we feel about that? What is O?
What does OPS stand for?
The observed. Our observed value, okay?
Is that always going to be x bar?
So for when we're dealing with one sample means,
Yeah.
it will be x bar, okay? But this is for almost all hypothesis tests, it follows this observed minus null. Okay? When we did a hypothesis for a proportion, what did we do? We did, well, one in the numerator.
P hat.
P hat minus
Oh, the P.
P, the P that was written in the null hypothesis. So it was P hat, which was our observed proportion, minus the P that was specified in our null hypothesis. Okay, so it's still this form of observed minus null. Okay, and the standard error for proportions test was that square root of P minus 1 minus P over to N square root thing. Okay, so it's the same idea, except what we're using for the observed, what we're using for the null, and what we're using for the standard error, the formulas have changed, but the concept remains the same. In all of these things, we're saying, if the null hypothesis were true, I'm expecting this value. What did I actually see? Something that was a little bit different. Is the difference between what I actually saw and what I'm expecting, is it a big deal or is it not a big deal? Okay? And that depends on the standard error. Okay? That's like the big picture thing that I'm hoping we can see and not get lost when we I guess do formulas and stuff. Okay. All right, so this is my test statistic, 1.398. What am I supposed to do with this? Okay. Well, when we did proportions, what did we do?
Resort to the table.
We would take this and look it up in the Z table. Okay. When we're doing it here, we look it up in a table, but this time, which table do we use? The T table, okay? So this is a key rule. Anytime you're dealing with means, you're always going to use the T table. Anytime you're dealing with proportions, you're always going to use the Z table, okay? So proportions, for proportions, look up the test statistic in the Z table, always. For means, look up the test statistic in the T table. Always. So how do we use the T table here? How do we use this? Okay, let's talk about that. Well, how many degrees of freedom do I have?
19.
I have 19 degrees of freedom. How do we get that again? N minus 1. Degrees of freedom is N minus 1. I have 20 in my sample. I subtract off 1, so my degrees of freedom is 19. So I'm going to copy a line from the T table onto the board here, okay? I'm going to look at the row that says 19 degrees of freedom. And what are the numbers I see there? 1.328, 1.729, 2.093, 2.539. Okay, at this point, I don't really need to keep going. And what are the column headings here? Okay, I'm just gonna, because it's a one-tail test, I'm going to use the row that says one-tail probabilities, okay? And two-tail probabilities are just double the one-tail probabilities, by the way. Okay, so no big deal. So the one-tail probabilities, I've got 10, 0.05, 0.025, 0.01, et cetera, et cetera, et cetera. Okay. This is good with everyone? What is the number that I have? What is my test statistic?
Negative 1.
-1.398. Okay. The T table is symmetric, so whether it's positive or negative, I could put negative numbers in front of all of these things, and the column headings would be the same. Okay. So I could just ignore the negative thing. And if I looked up 1.398, where would this fit in the lineup? If I had to line these numbers up.
0.10.
It's in between two numbers.
It fits in between this number and this number. Okay, 1.398 is in between 1.328 and 1.729. This is how the t-table works. If my test statistic ended up being exactly 2.093, the amount in my tail would be exactly 0.025. If my test statistic was exactly 1.729, the amount in my tail would be 0.05. And if it was exactly 1.328, the amount in my tail would be exactly 0.10. But my number is not any of those numbers exactly. It's 1.398. So how much is in my tail? Yeah. 7.5? Okay, that's a good, I like your thinking there, okay? But we're not going to be as specific, okay? Because you said 1.398 is between here and here, so I'm going to pick a number that's between 0.05 and 0.10, okay? And you said 7.5. Great thinking, except we're going to just be even more generic and safe than that. And we're just going to say, I have no idea what is there, exactly how much is in my tail, but I do know that it's between 5% and 10%, okay? So I'm going to say on my tail, whatever it is, it's less than 10%, but more than 5%, okay? Or if you wanted to write tail is between 0.05 and 0.10, that's fine, okay? And that's what we're going to say, okay? So 7.5% is probably a number that's very close to it, but we're just going to say, I don't know exactly what it is, but whatever it is, it's between 5% and 10%. Does that make sense? Is that good? All right. Let's say we did this and my test statistic turned out to be 1.1. How much is in my tail? Whatever it is, if my number turned out to be 1.1, I don't know exactly how much is in my tail, but it would be more than 10%, okay? And that's all we're going to say. So when we're looking up p-values with the table, we can't get exact values. We're just going to say it's between a certain range. It's between 5 and 10%. Okay. So my tail is between 5 and 10%, and because it's a one-tailed test, that will just be my p-value. My p-value, again, I don't know exactly what it is, but I do know it's less than 10%, and I do know it's more than 5%. What if the alpha I'm using, so if alpha is equal to 5%, what is the conclusion that I make? Do I reject, not reject? What do I do?
Not reject.
I not reject what?
The null hypothesis.
Yeah. So if my alpha is 5%, my p-value, whatever it is, it's more than 5%. So I do not reject the null. Okay. And that means, what does that mean if I do not reject the null? What's the answer to my question here?
We do not have evidence that the average height is not 72.
So at this point I say, if alpha is 5%, I do not reject the null, and I do not have evidence that the average height is less than 72 inches.
So, Mr. Mr. Chair, could you reiterate that, how we, came to that conclusion again?
How we came to-
The,
Okay, are you okay
P-value
with?
is greater than the.
So are you okay that the p-value is between 5% and 10%?
Yeah.
Does that make sense to you?
I'm good with that.
Okay. If my alpha is 5%, is my p-value greater than alpha or is it less than alpha? I'm asking you a question.
Yes, okay, so I'm looking at the p-value is less than alpha.
No? Okay, so my p-value, I don't know what it is.
But we don't know what the p-value is.
Right, but we do know it's between what values?
0.5% and 0.10%.
Okay, so don't say 0.5 and 0.10, okay? It's between 0.05 and 0.10, or it's between 5% and 10%, okay? But don't mix up the 0.5 stuff like that, okay? So it's between 0.05 and 0.10. Is that number more than 0.05? So here, we'll just simplify this. I've got a number in my head.
Right.
It's between 5 and 10. Okay? You don't know what it is. Is the number in my head bigger than 5?
No.
No, it is. It is. Okay? Because if I said it's between 5 and 10, it can be 6, it can be 7, it can be 8, or it can be 9, right? It could technically be 5.1, but we'll say we're not playing that game. Okay? So the number in my head is either 6, 7, 8, or 9. Okay? We don't know what it is.
Okay.
Or you don't know what it is, I do. So I'm asking, is that number bigger than 5? The number, yes. And that's what's going on here. Okay? The p-value, I don't know exactly what it is, but I do know that it's bigger than 0.05 and less than 0.10.
Okay, it's falling in that range.
Okay? So is it bigger than 0.05?
Yes.
Yes, it's bigger than 0.05. Is it bigger than 0.01?
Yes.
Is it less than, or is it bigger than 0.20?
Yes.
0.20.
No.
Is it bigger than 0.07?
No.
We don't know. That one we can't answer. Is it bigger than 0.07?
Oh, because it's not in the range.
Because, well, 0.07 is in between 0.05 and 0.10.
But we don't know the p-value.
We don't know what it is, okay? We just know it's between 5 and 10, 0.05. Does that make sense? Yes.
So for like a question on the test, would you have to do hypothesis test and the confidence interval? Or
No, you would just do one or the other, okay? So this is for a hypothesis test.
But either or would work, they're interchangeable?
The way I'm gonna set up the test is I'm gonna say do a hypothesis test,
Okay.
or do a confidence interval, okay? And answer these questions. Okay, so if I say do a hypothesis test, I might say, what are the hypotheses that you would use? What is the standard error that you would use? What is the test statistic that you find? What is the p-value that you get? Okay, those are all valid questions related to the process of doing a hypothesis test. Okay, yes?
I think you might have already answered this, but like when you write your p-value, so 0.05 is less than the p-value,
Mhm.
it's less than 0.10.
Uh-huh.
How do you, I don't understand like how you wrote that from how it's set up on the board.
Okay,
of the-
so my number 1.398
Yeah,
is in between 1.328 and 1.729.
yeah, I got that.
That's good, right?
Yeah.
Okay, this corresponds to this,
Mhm.
and this corresponds to this. So if my test statistic was exactly 1.729, my p-value or my tail would be exactly 0.05, okay? And if it was exactly this, it would be exactly this. But what I'm getting is something in between here and here. So my p-value would be in between here and here.
Yeah.
Okay, so the numbers up here go down and the numbers down here go up, so just be careful about that, okay? So I'm just saying it's gonna be between 0.10 and 0.05, or, I don't know, just by custom, we normally put the smaller number first, followed by the larger number. So I'd say it's between 0.05 and 0.10.
Okay. Yeah, I got that.
Is that okay?
Yeah.
Yes, these are all good, very good questions, by the way,
5
yeah.
and 10%, what is that of? You're saying it's in between, but 5 and 10% of what?
5 and 10%
The tail and
is the p-value, okay? So do you remember what a p-value is?
everything else.
Huh? The p-value? The p-value is a probability. okay? It's the probability of what? What is a p-value?
Observing the means, without being extreme or something like that.
Okay, the p-value is the probability of observing your data, or something more extreme, if what?
No hypothesis.
If the null hypothesis were true, okay? So what we're saying is, if the average height of Norwegian males really was 6 feet, if this was truly the average height, what's the probability that I survey 10 Norwegian males and get an average height of 71 inches or something shorter than that? Okay, the probability of getting 71 inches or something shorter than that, just because of the nature of random selection. Okay, when I choose things at random, I'm not going to necessarily get exactly what the average should be. The probability of that happening is between 5 and 10%. Okay, so it's not, when I say percentage, it's not a percentage of what, it's the probability of something happening, right? If I said, what's the probability, if I flip a coin, what's the probability that it lands heads?
50%.
You would say 50%. And if I asked you the question, 50% of what? There's nothing to answer, right? Maybe 50% of the time. I don't know. Okay, that would. So it's to answer a probability question. It's perfectly allowed to say a percentage, and not needing to say a percentage of what. Okay. How is this? Should we try an example? Yeah.
When you're setting up your standard error, is that a certain is that different than like, because last week you had like.
Yeah. So the standard error, this is the standard error that you use for one sample proportion hypothesis test. Okay. I'll try, I don't know if I'll have time today. If I do, I'll put like a summary table of all the standard errors and things like that. Okay. But, okay, so what I'm going to do here is I'm going to put an example up on the board. I'll ask a bunch of kind of questions to guide you along the way, and then I'll give you guys about 8 minutes to solve it, all right?
8 minutes?
I don't know.
Yeah, is our next test going to be more than an hour?
Your next test will be written for an hour. The way I gauge the...
If 8 minutes is one question.
Gauge the time is, I usually time myself, and then I multiply it by 8, okay? Alright? So if I can take the test in about between 7 to 8 minutes, I figure you guys can finish it in an hour, okay?
Little bitty bees out here.
Yeah.
Bitty chins, right?
Is that with all right answers, or like?
Yeah, of course, I get all the correct answers,
You
alright?
don't give us like a p-value of that, like, factoring in our mistakes and erased answers.
We should have I should have a race with some of the students, right? Like I give myself this and yeah.
Are we able to bring the formulas?
Yes, you can use a note card with formulas. Well, I'll talk a little bit more about this test, okay? And when I send out the email with the link to the lecture videos, I'll include can I send an attachment with these things? I don't know. Okay, if I can attach something, I'll send you a practice test with answers. Okay, and just so you guys are satisfied. But again, my practice test and the actual test will not be the same thing where I just change the numbers. Okay. So here I did an example with Norwegian males and how tall they are. Maybe your yeah, we'll not just say Swedish females. And, although that might be of interest to some of you. Now maybe it'll be like the average weight of a tomato or something like that. Okay, but or oranges. Have you ever gonna say oranges? Okay. So who knows what it's going to be? Okay. Similar concept. The concepts will be exactly the same, but something this. Okay. So let's do the average weight of a tomato. So, is the average weight of a tomato how much is it how many tomatoes in a pound here?
Probably 3.
Only about, I'm gonna say
Three.
4 or 5.
I was
Three
gonna
tomatoes
say
probably.
3.
Okay, so is the
3
average weight of a
combined.
tomato, we'll say 5 ounces. Okay, so that's a little bit more than, is the average weight of a tomato 5 ounces? Okay, so we gather data. Okay, a random sample. I don't know how to get a random sample of tomatoes, but somehow we've done it, okay? A random sample of, let's say,
30.
30, okay, 30 tomatoes. 30 tomatoes. The average weight is 5.9 ounces. The standard deviation is 1.8 ounces. Okay, is this evidence that the average weight of a tomato is not 5 ounces, 5.0 ounces? Okay, so the key here is not, so that hints at the one or two tailed nature. Alright, so the questions, leave yourself some space in your notebook, is what are the hypotheses? Okay. What is the standard error? What is the test statistic? What is the p-value? What conclusion do you make? And what does that mean? Oh. Alright, go ahead and try that out. Do you want me to put the answers up, or like just the numeric answer up, or not?
Not yet.
Not yet, okay. We'll wait.
We're not there yet.
Not there yet, okay. So good luck. I'll just walk around and see how you guys are doing. use an alpha of 5%. Okay, if you haven't gotten this part already, your hypothesis is that the average weight of a tomato mu is equal to 5 or 5.0, whatever you want to say. And the alternative is that mu is not 5.0, okay? Because, and the clue in our question was, is this evidence that it's not 5.0? So don't use less than or greater than. Use is not. And this means we've got a 1 or 2 tail test. This would be a 2 tail test. So not equal to sign means 2 tail test. The S in the standard error formula is the standard deviation of the sample, yes. Okay, I know some of you guys are still working.
No.
No? No?
No, we are.
You are, yes.
See, I think you better move that number in 8 instead of timesing by 8, like timesing by 9 for the test.
13.
Or 13 for like me.
Okay. Let's keep going here. Okay, what is the standard error that we use for a hypothesis test for one mean based on one sample? Okay, so this is for, our test is one mean, for a hypothesis test, mean of one sample, right?
Right.
Okay, because based on the type of problem that you're using, the standard error changes. In this case, it's going to be S divided by the square root of N. So I've got 1.8 divided by the square root of 30.
2.32863.